We have already looked at the static characteristics of sensors, and those were characteristics when we said that the input is a constant, and we're not really interested in how much time the sensor takes to respond to the input, but we are only interested in the steady state response of the sensor, or the response once the sensor has settled down. But now we're going to look at dynamic characteristics, and this is the place where we are actually going to concentrate on uh, the situation where the input itself is changing, or we are looking at a situation where the input has changed, and we look at the sensor, at the transient response of the sensor, the change of the output of the sensor before it stabilizes. So, by dynamic characteristics, basically what we are looking at is the behavior of a sensor as the inputs are changing. Now, the way to really characterize the dynamic characteristics would be to use differential equations, as I've shown on the screen, for the sensor. We could also use a frequency domain representation where instead of talking about the time domain behavior, which is represented by the differential equation, we can look at the frequency response of the sensor, where we are looking at what happens when we give inputs of different frequencies to a sensor. And now, of course, the equations that are shown on the screen are quite complicated, and we want to make it easier to analyze and understand how our sensors behave. So, usually, what we tend to do is we tend to approximate the behavior of our sensors, and we do that by calling our sensors either a zero order or a first order or a second order system. And we do this basically by um, making this n here either 0, 1, or 2. So 0 order, first order, and second order corresponding to the different values of n. Now, what that does is it gives us a way of analyzing sensors that is simple and intuitive. More complicated sensors can be broken down into parts that are either zero order or first order or second order, right? So sensors can be approximated by as a zero order or a first order or a second order sensor, and we analyze them as such. And in the next few videos, what we are going to do is we are going to take a look at the response of our sensor if a sensor is one of these types. Now, how do we evaluate the response of a sensor? Now, as I said, if you're going to evaluate the response of a sensor in response, if you're looking at the frequency response, then what you can do is you can just give a sinusoidal input and look at the output. So that would be one way of analyzing your sensor. Another way of analyzing your sensor would be to give different kinds of inputs to the sensor. So you could give a step input. A step input is an input that changes suddenly. So the input is at a particular value, and suddenly the input changes to another value. What happens to the output? Does it also change suddenly? Does it have the same shape as a step? Or is there a much more slower uh, response? Now, one situation in which you can see these kinds of responses is to think about you sitting in a car and driving on the road, and let's say you're going at some speed, and suddenly there is a, a, a break in the road. Okay, so the road is going like this, and suddenly there's a dip in the road, and then the road goes on like that. I know you won't find that in real life, but it's an approximation of a ditch or something on the road. Okay, so if you're going in the car like that, and if when you're sitting in the car you also dip suddenly as the road dips, that would be a zero order response. If the if your if you your seat actually moves slowly to the final value, not suddenly, like the car, that would be a first order response. And sometimes what you would see is because of the dip, the seat actually goes through some oscillations before it settles down on the final value, and that is the second order response. So we'll study these in a little bit more detail in the next few videos.